Hello, everybody. I'm super excited to be here at P99 Conf. Welcome to my talk about the 1 billion row challenge, or 1BRC for short. And this was a challenge which I organized with and for the Java community earlier this year. It kind of went viral, and the task was, well, to process 1 billion of rows in a text file, and we will learn more about the details in a bit. And in this talk, I would like to talk about what I learned from the challenge, but then also what the community actually did to implement this task as fast as possible. So I want to touch on some of the technical details, and of course, we will see how far people eventually got. So that's the agenda for the next 30 minutes or so. Just briefly on myself, I work as a software engineer at a company called Decodable, where we build a managed platform for stream processing based on Apache Flink and Debezium. All right, so let's get into it. And as I mentioned, this was running earlier this year, precisely in the month of January. So I kicked this off on January 1st, and I kicked it off with a blog post where I announced the challenge, and I also had a tweet about it. And we will, see later on what exactly the challenge was about. But so this is how it started. And then quite quickly, it, got picked up. People started to implement the challenge with all kinds of languages. So initially it was meant for Java, but then also people did it in all kinds of other languages, such as Rust or Golang, even COBOL and other languages like that. Tools like org, databases like Postgres, Snowflake, people wrote about it. So there was this article on InfoQ, which was the most read article on InfoQ for the first 6 months of the year. There was this guy, Prime, I guess many of you know him, who covered it in his live stream. So it kind of went viral, I would say. And during that time, I learned quite a few of things about the technical side of things, but then also about just how you actually go about, printing a certificate of achievement for 165 people. So that's what I learned. I learned how to send out T-shirts and coffee mugs to the winners, because I wanted to have a prize in the end for them. So I, sent those prizes to people in the Republic of South Korea, Southern America, the US, and really pretty much all over the world. Now, why did I do this challenge? And first of all, well, I thought it would be interesting to learn something new. So I had a bit of a, low time between the holidays, between Christmas and New Year's Eve. So I felt, okay, it would be nice to learn something new in terms of Java. So what is there in terms of new features, new capabilities of newer Java versions? But then, of course, also, I thought it would be nice for other people to learn something new for them as well. So that's why it is a challenge. Of course, it's always nice to, have some fun. So you just don't want to go and read something. And the challenge, like a friendly competition, that's, I would say, a fun way to do something, to find out something new. And also, the idea was to inspire others. So more than about the competition, this was really like, just to work on something together and to inspire each other. And this is what happened. So people actually teamed up for solving the challenge together. And then, of course, there was there is this myth, I guess, which I also wanted to debunk a little bit. So people still oftentimes or sometimes have the perception that Java is slow and maybe like old school. And this is what I wanted to help to debunk. And I think if we go and see later on how fast people actually went in the end to process those 1 billion rows, we will see, well, actually, I think this myth is debunked. All right, so then let's dive a little bit into what actually that challenge was. And it's pretty much all in this picture here, and it's all pretty much also in the name, right? The 1 billion row challenge. So the idea was, well, we have a file, and I mean, it's kind of like a CSV file. The separator is a semicolon instead of a comma, so it's more like a, a semicolon separated file. And now it has just 2 columns. There's a station name, so something like Hamburg or New York City, Helsinki, and so on. And then for each station name, or for each measurement, I should say, there's a temperature value assigned. And the task is very simple. You should write a program which processes that file as fastly or as quickly as possible. And you need to calculate the minimum value, the minimum temperature value per weather station, the maximum value, and the average value. And the only caveat is, well, there's 1 billion rows. So this file is quite sizable. If you have it on your disk, it's about 13 gigabytes. So it's quite a bit of size to process. And the task, well, is, again, as I mentioned, to make this happen as quickly as possible. That's pretty much what the task was. In terms of the rules of engagement, first of all, this was meant for the Java community. This is the ecosystem I would like to, proliferate the knowledge about. I'm part of it, and it's just what I know the best. So it also was a little bit like just for practical reasons, instead of having to set up all kinds of tool chains, finding out how to set up Rust compilers and Golang compilers and so on. I wanted to limit it a little bit, so just to make the life a little bit easier for myself. But then within Java, you could use any version. So you could use the latest version. So you could use preview builds, which comes back to this notion of learning something new, right? Because all those new versions and maybe like the early access builds, they come with new features, maybe preview APIs such as the vector API or the foreign function memory API. And this was exactly the idea, to see how we can employ those newer APIs for the purpose of this challenge. You were not supposed to have any dependencies. I mean, if you just were to pull in some sort of, CSV parsing library, where would be the fun of that, right? So just have a single self-contained file, so you have to solve it by yourself. And then very importantly, you could copy code from other people. And now, of course, you shouldn't just go and resubmit somebody else's implementation. That wouldn't make that much sense, right? But you definitely could take a look and see what they do. And this is what people did. And it goes back to this notion of being inspired, learning from others, right? So people could take up tricks from other people, and that's also what happened. And sometimes, as I mentioned, they even teamed up and submitted like a joint solution. In terms of the execution, I ran this on quite a beefy server. I did 5 runs of each submission. I discarded the slowest and the fastest one, and then I took the average value of the remaining 3 runs, just so as to make sure that essentially the file is read from the page cache, so to avoid any impact on I/O, and also just to have like a representative value. All right, so then let's see how we actually can go and solve this. And this is my baseline implementation. And I would say it's pretty much canonical standard Java code as I would write it, and as I guess many other people would write it, using the Java Streams API. And this is what's happening here. So we are using this files.lines method, which gives us a stream with the lines of a file. So this is where we read our input. And then we map each of the lines. So essentially we want to split this measurement row at the semicolon, and then we want to group it by station, right? And this is where this collector object comes into the picture. So we have a collector which takes care of adding a new row into the aggregation. So we keep track of the minimum value we've seen so far. We keep track of the maximum value we've seen so far. And then we also, track sum and the count of the samples we've seen, so that later on we can determine the average. So that happens when a new row gets added to that aggregator. I also may have to merge multiple aggregators if I run this in a parallel concurrent way. So this is what's happening here. Again, just propagating min, max, sum, and count from those 2 aggregators. And finally, if I want to omit the aggregation for one particular station, well, I propagate the min value, I propagate the max value, and then for the average, I just divide sum by count. Pretty much canonical Java code, as I said. And this ran on that box, which I had in roughly 5 minutes. So not too bad, pretty decent. And if this is like a one-off thing, I guess it might be good enough. But of course, it's not good enough for the purposes of this coding challenge. So let's see how we actually can go and make this a bit faster. And the idea is I want to talk on some of the tricks people employed to give you some ideas what you can do to make this fast. And now with such a challenge, it's always important. Well, people need to pick it up, right? So maybe just everybody ignores it. Nobody takes part in it. And thankfully, Roy Van Ryan, who is another Java champion, he realized the potential of the idea. And he very quickly came and submitted just some sort of improvement to the baseline implementation. And the idea for him was just, well, to show to others, well, this is something interesting, something exciting. So let's all go and participate. And, then it's kicked off. So people saw he did it, and then others came and also submitted their implementations, and they got faster and faster over time. But big shout out to Roy for being the first one. So let's talk about parallelization. First thing, which is kind of obvious, right? So we have all those many cores in our CPU. So on that box, I had 32 cores, 64 threads, out of which I actually used 8 for the measurement purposes. But we want to leverage those cores, right? So we don't want to be just single-threaded. In the simplest case, we can take this initial implementation which I had and just add a single method call. We just can add this parallel call. And this is all which is needed with the Streams API to, well, take advantage of the calls which are available to us. And this brings it already down to 71 seconds just by adding this single method call. Now, I ran this with 8 cores, as I mentioned, and now if you do the math, this isn't 8 times faster. So somehow we still don't use all our 8 cores all the time. And the reason for that as well, this parallel call, this applies to the mapping and the aggregation phase here, but it doesn't apply to the I/O phase. So this files.lines, where we read the file from the memory, this still happens sequentially. So we don't leverage the CPU cores all the time, just for like a part of the runtime of this pipeline. So let's see how we can change that. And now this is where this new API, or relatively new API, comes in, the for a function and memory API. It's defined in one of the Java enhancement proposals, 454. It's an API which allows you to interact with native memory, so off-heap memory, which isn't managed by the JVM, and then also to do native calls as a replacement for JNI, which isn't that interesting for our purposes here. But the off-heap memory, that's interesting, because now we can use this API to essentially memory map the entire file into a memory chunk managed fully by ourselves. And thanks to that new API, we can memory map the entire 13 gigabytes. So before, you could memory map files, but not more than 2 gigabytes at once. So this is where this new API comes in handy. Just to give you some idea how this could look like, well, first of all, we want to determine the degree of parallelism. So we essentially query how many processors do we have at our disposal. And this is how many chunks we want to process at once. So 8 in this case. Then I open this file, and there's now this notion of an arena. And an arena essentially is a memory section, which is given to us and which we can manage by ourselves. There's different kinds of arenas. In this case, I'm just going with this global arena, which is, well, globally accessible from everywhere in the program. And this is where we memory map this file into. Then I need to split up my work. So my 30 gigabytes of input file, I need to split this up. And now, well, the first iteration would be, well, just let's split it up into 8 equally sized chunks, right? Now, the thing is, what happens, well, in all likelihood, we will have our chunk boundaries in the middle of a line, right? And that's not very desirable. Our worker threads, they should work on complete lines. So what we do here is, if we have this first approximate boundary, then we just keep going until we have seen the next line ending byte, and we take this as the end of the current chunk, and then our next thread will start at the next line. So we have nicely isolated the lines between our worker threads. Then we go, we send off our threads, we do the processing, the parsing of the lines, and we will, sorry about that. Then we go off and do the processing of our threads. So we, organize our 8 threads. They work on the different chunks, and they do the actual parsing of the file. And we will see later on how that could happen. And finally, well, we want to start the threads, and we want to, once they each are done, we want to join them together. Now, this brings us down quite a bit. So this really takes advantage of all the CPUs we have. But still, what happens actually is, well, one of those 8 threads, it will always be the last one. So we still have that situation that essentially 7 of our cores are waiting for the last one to also be finished. So what people actually did in the end is they didn't split the file into just 8 chunks, but instead they split it into much smaller chunks. And in the end, they arrived at a chunk size of 2 megabytes. And this was, well, because actually, as it turned out, this CPU where it was running this on, it had a second level cache of 16 megabytes. And now, well, having 8 worker threads working on 2 megabytes chunks, it just made the most efficient usage of the second level cache in terms of, like, prefetching stuff and so on. And this already shows to what a specific level in terms of CPU architecture and characteristics of the machine people went down to while optimizing it. All right. So the challenge was running. And of course, if you have this kind of thing, there's always some sort of conspiracy theories going on, right? And I have a few ones here. So people asked, so, hey, is this actually like, you had this problem at your workplace at Decodable and you just couldn't solve it out. So you couldn't solve it. So you farmed it out to the community. And well, I can tell you, no, that was not the case, because I had so much work with running this challenge during the month of January. So this would have been like the most inefficient way for solving that problem. Is it an ad for GraalVM? Many people solve this with CRM? No, it just landed itself very well to that problem. Is it an ad for Epic, the CPU which I was using there? Also no. So people have all kinds of conspiracy theories, but really, I just organized it as a fun thing for and with the community. The other thing which I found interesting, I'm on Hacker News every now and then, I have to admit it, and there always is the person on Hacker News. For them, it's very trivial, right? So they just say, this is a trivial problem, and like everybody who just can program a little bit, they can solve this in like 2 hours. And then you have like all the people from the community, like Alexei Shipilev or Cliff Click or Thomas Würtinger, who leads the GraalVM team at Oracle, who spent the entire month of January like really optimizing this down to the instruction level. But still, you have this guy who just thinks it can be done in 2 hours. So very interesting to see the different reactions to this sort of thing. All right, so we have spoken about parallelization. So let's talk a little bit about the actual parsing. So what happens if we want to process the individual lines of our file? Now, and again, this is some code which I would write, I guess. And this is just, instead of, using like a regular expression to parse and split up the line, we just can process our bytes one by one in terms of a state machine. And this is what we see here. So essentially, we just, we read the bytes which come in for our current line. We keep track of in which state we are. So are we before the semicolon or are we after? So that's, depending on that, we either assemble the name of the weather station because those bytes make up the name, or we assemble the temperature value. And now, depending on where we are, we feed the current byte into different kinds of buffers. And then if we have reached the end of a line, so we see the line ending character, well, then we process those buffers. We take the bytes which form the station name, put that into a string, and the same for the temperature value. And this is what happens here, actually. And this is very interesting because it showed how people took advantage of the characteristics of the particular data set. So in the data generator, which I had given to people to produce that 13 gigabytes file, the measurements always had exactly one fractional digit. So from minus 99.9 up to plus 99.9. So people realized, we don't actually have to handle this as a true floating point value. Instead, we just can handle it as an integer value. And then at the very end, if we process the output, we can, divide maybe by 10 or by 100. So we just can consider that as an integer problem. And then, of course, avoiding floating point mathematics is much, much faster. And this is what we see here. And now doing all that, this gets us down to 20 seconds. So already one order of a magnitude faster than my initial baseline implementation. And I would argue the code still is pretty well readable. So, it's maintainable, it's readable. So it's pretty good. And in your everyday job, you might end there. But then if this is a coding challenge, well, then of course you need to keep going. So what can you do to make it faster? Well, instead of processing bytes one by one, you can try and process multiple bytes at once. So we are back to the notion of parallelism. So, we scaled out to multiple threads, taking care of all the cores which are available to us. But then also we should advantage of the instruction sets which our CPUs have. And in particular, they have those instruction set extensions called SIMD, single instruction multiple data, which essentially apply the same operation on multiple values at once. And this is what we see here. So let's say we are looking for the line ending character. Instead of comparing byte by byte, we can call this methods from the Java Vector API, which compiles down into those SIMD instructions. And now this will apply this comparison operation to 8 bytes or maybe even 16 bytes all at once. And of course, this will give us a very significant improvement. And now, traditionally with Java, we didn't really have any means of making use of those SIMD instructions explicitly. So the compiler sometimes would auto-vectorize code for us, but we didn't have any means of doing this ourselves. And now with this new API, the Vector API, which is still a preview version, we actually can do that, and still then our code is portable. So this will compile down into vectorized code on Intel, but also on ARM machines. And suddenly, I would say we are even in a better position than, let's say, a C programmer, because, we have vectorized code, but it's actually portable. So we don't need to think too much about the underlying CPU architecture. So that's single instruction, multiple data across multiple bytes. And we also can apply the same principle actually within a register. So that's called SWAR, SIMD within a register. And the idea there as well, we can handle, for instance, 8 bytes. They form together like one long value, right? And now with the right level of bit shifting and masking, we can actually apply the operation on all those 8 bytes by just applying it to a single long. So we do the same thing, applying the same operation to multiple values. And you see already the code gets more dense and dense, right? So that's probably not something I would have come up with, but people in the challenge thankfully did. So this gets harder to maintain and so on, but it's getting faster and faster. And what's interesting also is something is missing here on this in this particular code, and this is there's no conditionals, there's no ifs, no while kind of loops, for instance. And this is very interesting and very powerful because it benefits very much from how our CPUs are working, and I will touch on that in a second. Just a little excursus. I have another example here. So this shows the same sort of, branchless programming to find the first 0 byte in a long word. And you can follow the math here if you like on the right hand side. You can go to the QR code and find this example. It's by Richard Startin, who also has, by the way, a talk here at the conference. And then you will see how this, kind of magic bit mangling actually returns the first 0 byte in a word. So why is branchless programming so interesting? Well, it's interesting or useful because our CPUs, they operate in a pipelined way. So this means whenever we execute an instruction, it has those phases. The instruction is fetched from memory, it's decoded, it's executed, the result is written back. Now those phases, they happen concurrently for multiple instructions. So while we decode our one instruction, we already can go and fetch the next instruction. And doing this again in parallel obviously makes things faster. But for this to work, we need to know, or the CPU needs to know which will be this next instruction, right? Otherwise it wouldn't know which one to fetch. And this is why this branchless programming is so useful, because if you have no ifs, well, then it's always clear from the program what the next instruction will be. Whereas if we have conditionals, well, then there's what's called the branch predictor. It makes an educated guess of what might be in the next instruction, and it might be right or it might be wrong. And of course, if it's wrong, then we would have to flush this entire pipeline and like reprocess, recompute values, which makes us slow. So that's why branchless programming is very interesting here. If you want to learn more about all those kinds of things, definitely check out this book. I learned about it during the challenge called Hacker's Delight. It has all those tricks, all those algorithms, which really teach you how to do this. So here in this talk, I just really want to give you the idea, okay, those things exist. And I realize it's like probably impossible to really follow along all the individual steps. But, going to resources like that, you will be able to really learn and deeply understand how those things work. All right, so that's parallelization, that's parsing, and there's one more thing I want to touch on, and that's bookkeeping, because, well, we need to aggregate our values essentially into some sort of map, right? In the initial example, essentially, I have a hash map keyed by weather station name, and then within those hash values in my hash map, then I aggregate the values per station. Now, Java hash map, it's a generic data structure, so it works well for many use cases, but if we can take advantage of the specific characteristics of our problem, we actually can come up with a better data structure just tailored for the particular purposes here. And this is what many people did. So they didn't use a regular map, but they came up with their own map implementation. And I find it very interesting because it's actually relatively simple to follow. So the idea is, well, you put your values into an array, essentially. So we have this array of buckets. Now, if you want to put a value into this map structure, we take the hash code of our key, so the bytes which form up the station name, we take the hash code from that, and this is what we use as an address or as an index in our array. And we take it, modulo with the length of the array, so just to make sure we always have an index within the array size. So we take that, and now we want to check, is something at that particular array index already? And if it's not the case, well, then we know, okay, we have the first value which we need to put into the map for this particular key. So, then we will just create a new aggregator object, add our value into it, and store that aggregator object at that particular offset in the array. Otherwise, if something already exists at that offset, well, then we need to fall back to the slower code path here. And this is, we need to actually compare, is the name which we have incoming, is it the name of that aggregator object at that array position? Because, well, it's a hash function, so multiple keys could have the same hash code, right? So we need to compare. And now, if our comparison says, okay, well, the name you want to add, this actually is at this index, then we are good to go. Otherwise, we will just keep going. So we'll go to the next element in the array and see, is this one the bucket we want to allocate to? So it could either be free or it's another bucket and it's ours. And this is why this is called linear probing. So, we just probe in the array until we have found our aggregator to which we want to add. And again, this shows how much people took advantage of the specific data set because, well, in this generator which I had provided, this used about 400 something different station names. So people actually chose hash functions which were collision free for those 400 station names. So the most implementations which people did, they actually perform very well for that particular data set, but maybe not as good for other key sets. And some people then also optimized actually for a more generic data set. All right, so let's just briefly, touch on a few more things, what else people did. So GraalVM, coming back to the conspiracy theory. So I guess, people familiar with Java, they will know GraalVM. It's both a JIT, a just-in-time compiler, and also an AOT compiler, an ahead-of-time compiler. Now, what I really recommend to you is try out using GraalVM as a JIT compiler, because it essentially is just means of configuration. Run it on a JDK, run your application on a JDK, which uses GraalVM as the JIT compiler, and it may be faster than what you had before. And in this case, for this workload, this was actually the case. And so essentially, you get a nice improvement, a few percent, essentially for free, just by using, GraalVM as a JIT compiler. So really easy to change, nothing to lose. The other thing is, well, using GraalVM as an AOT compiler. Then, of course, it comes with different considerations. Your program needs to be enabled to be compiled into a native binary. But then, if you have done that, then you will save, in particular, in terms of startup time and in terms of how far people got in the challenge, saving those couple of 100 milliseconds when the JVM boots up, because, for instance, we don't need to actually compile any code at runtime. This really made all the difference. And then another thing people did as well, they just disabled garbage collection. So there's this epsilon garbage collector, which doesn't do any garbage collection. And again, I found this very interesting because, well, if you have such a problem where we can, solve it in a way that we don't actually allocate any objects in our application runtime only at startup, then we just can turn off we can turn off the garbage collector, which means we don't need to spend any CPU cycles on the garbage collector, which means we can use the CPU cycles for our own purposes. So this could, for instance, be interesting if you were to program on very short-lived applications such as a CLI tool. So worth trying out. Many other things, and I don't really cannot go into all of them. I just want to mention one of them, which I found particularly interesting, and this is what we see on the right-hand side here. So in the leading implementation, there's this inner processing loop. It actually shows up three times in the code in a row. And now you would think, well, this code is, sequentially written, so this has to be executed sequentially. But actually what happens is, as there's no data dependency between those three loops, the CPU will be able to execute this again concurrently because it has multiple execution units. Now, this means essentially this code, we look at it here and it seems it's sequentially happening, but actually it's happening concurrently. So super interesting. And again, really taking advantage of the specific CPU and its behaviors. Now, of course, I guess you are interested, how far did people get? And I don't want to make a secret. So on those 8 CPU cores, the leading implementation from Thomas Wertinger, as I mentioned, from the GraalVM team, they went down to 1.5 seconds. So I find this really impressive to think about it. Process this file with 13 gigabytes of size and with 8 cores getting down to 1.5 seconds. So pretty impressive. As you can see here, most of the leading implementations were all based on GraalVM. The fourth one, this is actually by Serkan. This is the fastest one on the JVM with 1.8 seconds. Also really cool. Of course, I wanted to take a look at how does it happen, how does it look like if I take all my 32 cores, all my 64 threads, and then we get down to 300 milliseconds. And I mean, I don't know about you, but I think this is really mind-blowing to be able to process a file with that size in mere 300 milliseconds. Really cool. I want to give a brief shout out to the community. So really, I mean, I started this by myself, but it really grew over my head. I had no idea what I would get myself into, and it wouldn't have been possible without the amazing community which formed around 1BRC. So people, helped to create a test kit, which we can see here. So just to make sure that implementations actually are correct. So, you don't want to only be fast, you also want to produce the right results. So people did that. People helped me with setting up and configuring the environment so that it actually, gives us meaningful results. They did all kinds of scripting so that it was actually very easy to run all those implementations. So massive thank you to the community for doing all this. Now, of course, the question for you is, should you do any of this? And well, of course, always the question is, it depends. So if you work on, let's say, a regular enterprise application, I don't know, probably you don't want to go as far. You can, for instance, take a look at this particular implementation. Again, go to the QR code. This is one order of magnitude faster than my baseline implementation. So this runs in about 20 seconds or so. And it still is very well readable, very well maintainable, I would say. So this is a reasonable thing to do. But then, of course, if you want to, go down to another level, to another order of magnitude, so you want to go down to 1.5 seconds, this is where you need to do all those bit shifting and SWAR and whatnot tricks, right? And the question is, it depends. Well, should you do it, right? So you should do it if you build a database, for instance, in any case, or if you want to, succeed in this sort of challenge or win a coffee mug, then you should do it. And also you should do it if you want to get hired into the GraalVM team, because I just learned this the other day. One of the people who came up with a very, very interesting parsing implementation. Actually, they, joined the GraalVM compiler team now and work on auto-vectorization there. So really cool to see. It grew quite a bit beyond Java. So initially, I meant this for the Java community, but people did it in all kinds of languages and ecosystems. There's this great show and tell. So I didn't really have the capacity to evaluate all those implementations, but we have this show and tell section there. So you can take a look at how people solve this on Rust, in OCaml, in Golang, Python, and so on. So definitely worth checking out. And that's pretty much what I had in this talk. Just going back to the original premise. Well, Java is slow. I don't think so, right? I really think this effort could make the case that we can be super fast and super competitive with Java and the JVM, or compiled down into a native image with GraalVM. And now, while I didn't measure any other languages, I just didn't really have the capacity. I'm really sure and confident that Java is very, very up high there, because just by seeing how, what people did, counting CPU instructions and so on. So definitely super competitive. That's all I had for you in this talk. I wish you a very nice, very informative P99 conf, and have a wonderful day. Thank you so much.